Welcome to an exploration of one of the most famous paradoxes in physics and mathematics, the Achilles and tortoise paradox. Imagine the legendary Greek hero Achilles racing against a slow tortoise. The tortoise gets a head start, and surprisingly, an ancient paradox claims Achilles can never catch up. Let's carefully set up Zenos' paradox and understand why it seems so puzzling. Suppose Achilles runs 10 times faster than the tortoise. This seems like an overwhelming advantage. However, the tortoise gets a 100-meter head start. Now the race begins. Here's our starting position. Achilles begins at position 0, while the tortoise starts at 100 meters ahead. Now comes the paradoxical reasoning that puzzled philosophers for centuries. By the time Achilles reaches the 100-meter mark where the tortoise started, the tortoise has moved forward to a new position. The time for Achilles to reach the 100-meter mark equals 100 divided by Achilles' velocity. During this time, the tortoise moves a distance equal to its velocity times this time, which is 10 meters if Achilles is 10 times faster. In step 1, Achilles reaches the 100-meter mark, but the tortoise has moved 10 meters ahead to 110 meters. When Achilles reaches 110 meters, the tortoise moves to 111 meters. This process continues infinitely. Step 2. Achilles must cover another 10 meters to reach 110 meters. Step 3. Now Achilles must cover one more meter to 111 meters. Step 4. Another 0.1 meters. The distances get smaller, but never reach zero. Zeno argued that since there are infinitely many steps, Achilles must complete infinitely many tasks, which seems impossible in finite time. Let's analyze this paradox mathematically using modern tools. The key question is, can we add infinitely many distances and get a finite answer? Let's find out. The total distance Achilles travels is 100 plus 10 plus 1 plus 0.1 plus 0.01 and so on forever. We can factor out 100 to get 100 times the series, 1 plus 1/10 plus 100th, and so on. This is what mathematicians call a geometric series, where each term is a constant ratio of the previous term. A geometric series has the form a plus ar plus ar squared plus ar cubed, where r is the common ratio. When the absolute value of r is less than 1, the infinite sum equals a divided by 1 minus r. This is a profound result. Applying this formula with r equals 1/10, we get 100 times 10 over 9, which equals 1,000 over 9, approximately 111.11 meters. This graph shows how the partial sums approach the limit of 111.11 meters. Each step adds less distance, converging to a finite value. Now let's examine the time required for each step of the pursuit. If the distances sum to a finite value, what about the times? Do they also sum to something finite? Let's assign concrete values. Achilles runs at 10 meters per second, and the tortoise at 1 meter per second. The first step takes 10 seconds for Achilles to cover 100 meters. The second step takes 1 second to cover the next 10 meters. The third step takes 0.1 seconds to cover 1 meter. The total time is 10 plus 1 plus 0.1 plus 0.01 seconds, and so on. This is another geometric series with the same ratio, giving us 10 times 10 over 9. The result is 100 over 9, approximately 11.11 seconds. Achilles catches the tortoise in finite time. At exactly 11.11 seconds, Achilles reaches the same position as the tortoise. The paradox is resolved. The resolution lies in understanding mathematical limits, a cornerstone of calculus. A limit describes the value that a sequence approaches as we take more and more terms, even infinitely many. We write the limit as n approaches infinity of s sub n equals s, the limiting value. For our paradox, s sub n equals the sum from k equals 0 to n of 100 over 10 to the k. As n approaches infinity, this sum approaches 1,000 over 9, even though we're adding infinitely many terms. The key insight: infinitely many steps can still produce a finite result when those steps get progressively smaller. The paradox reveals a fundamental truth about the nature of motion. Zeno's fundamental error was treating continuous motion as if it were made up of separate, discrete steps. In reality, motion is continuous and smooth. Achilles doesn't stop at each point, he flows through space. This graph shows continuous motion as a smooth line. Position increases continuously with time, not in jumps. Position as a function of time equals velocity times time. This is a continuous function. For Achilles, position equals 10 times t. For the tortoise, position equals 100 plus t. To find when they meet, we set their positions equal, setting 10t equal to 100 plus t. Subtracting t from both sides gives 9t equals 100. Solving for t gives 100 over 9 or 11.11 seconds, exactly matching our infinite series result. Here both position functions intersect at the red dot, 11.11 seconds and 111.11 meters. This is the meeting point. The paradox teaches us something profound about space and time. Between any 2 points in space or time, we can always find another point. This is infinite divisibility. However, infinitely many divisions can still sum to finite distances and times, as we've seen. This line can be subdivided infinitely, yet it still has a finite length. Each subdivision gets finer and finer. This raises a deep question. Are space and time truly continuous in nature, or do they have a smallest unit? In classical physics, we treat space and time as perfectly continuous, infinitely divisible. However, quantum physics suggests there might be a smallest length, the Planck length, about 10 to the minus 35 meters. The Planck length equals the square root of h bar times g over c cubed, approximately 1.6 times 10 to the minus 35 meters. The resolution of Zeno's paradox laid the groundwork for modern calculus and physics. Newton and Leibniz independently developed calculus in the 1600s to rigorously handle infinite processes and continuous change. Velocity is defined as dx by dt, the limit as delta t approaches 0 of delta x over delta t. This is an instantaneous rate of change. This allows us to define velocity at a single instant in time, not just as an average over an interval. The tangent line to a position curve at any point gives the instantaneous velocity at that moment. This is the derivative. All of classical mechanics, including acceleration, force, and energy, relies on the calculus concepts that resolve Zeno's paradox. Acceleration is the derivative of velocity. Force equals mass times acceleration. Work is the integral of force over distance. The concept of convergent series appears throughout physics. Many physical quantities in nature are computed using infinite series that must converge. For example, e to the x equals 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, an infinite series. Sine of x equals x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, continuing infinitely. These particular series converge for all real values of x, giving us exact values from infinite sums. This graph shows how adding more terms in the sine series approximates the true sine function better and better. The lessons from this paradox have profound real-world applications. GPS satellites use Einstein's relativity in calculus to account for continuous motion and time dilation. Computer graphics render smooth motion by calculating positions at discrete time steps, approximating continuity. Movies show 24 or 60 discrete frames per second, but our brains perceive this as continuous smooth motion. Numerical integration methods break continuous problems into many small steps, just like Zeno's paradox. An integral from a to b of f of x dx is approximated by summing f of x sub I times delta x for many small intervals. Beyond mathematics, this paradox has deep philosophical implications about reality. The paradox forces us to ask, is reality at its deepest level continuous like calculus assumes, or discrete like quantum mechanics suggests? The classical view, validated by the resolution of Zeno's paradox, says space, time, and motion are continuous. But quantum mechanics reveals discrete energy levels, quantized phenomena, and possibly discrete space-time at the Planck scale. We have two competing views of reality, the continuous classical picture and the discrete quantum picture. Both are needed. Modern physics uses both concepts. continuity at everyday scales, and discreteness at quantum scales. Let's work through a complete numerical example to solidify our understanding. Imagine Achilles runs at 5 meters per second. The tortoise crawls at half a meter per second, 10 times slower. The tortoise gets a 50-meter head start. The distance series Achilles must cover is 50 plus 5 plus 0.5 plus 0.05 meters, and so on. This sums to 50 times 10 over 9, which equals 500 over 9, approximately 55.56 meters. The time series is 10 plus 1 plus 0.1 plus 0.01 seconds. This sums to 10 times 10 over 9, which equals 100 over 9, approximately 11.11 seconds. Let's verify this using the continuous motion equations.